Hi dear students and viewers, welcome back to our channel Vinay Kumar Basics of Physics. Dear students, in this video we are going to discuss about the JEE NEET EAMCET syllabus related to the chapter waves and sound. Clear? So this is the first chapter, you have to remember that. So here I am going to upload all the videos first year and second year alternatively, so kindly notice it. So now let's come into the point. What is mean by wave and what is mean by wave motion? What is the wave? The wave, that should be nothing but a disturbance created in the medium and that can be transfers the energy from one place to the another. That is what we call a wave. For example, one steady water it is there, in that you can drop any pebble or any stone. Then what you observe, the water ripples can be formed, and there is one iron metal it is there, like telephone pole or any rod. You can strike it with a rod or any stick or with any pebble or any stone like that. Then that iron metal also can vibrates. Clear? So it means that what, when we suddenly dropped a stone into the water, up to that time the water is very steady, and once the stone is entered, there is some disturbance is created. That disturbance can be here nothing but wave. Why? Because due to disturbance some energy is transferred from one place to the another place. We can easily observe that if you can keep any leaf on the water surface, then it can float like this. You can make some dance. So it is nothing but what? A wave. So simply what you have to say, wave is nothing but a disturbance created in the medium that can be transfers energy from one place to the another place. There are number of waves are there. Number of light waves, sound waves, ultrasonic waves, infrasonics. So many kind of waves are there. Clear? And now here coming to the point. What is mean by wave motion? What is mean by wave motion? So here, when a body is going to be vibrated, in that the particles are vibrates at their respective positions. For example, here this is the one rod it is there. If you can vibrate at this position by striking it with any hammer or anything, whatever may be, if you can strike it, then you can find some vibrations are formed. Due to the vibration, some sound is produced, and the vibrations are transferred from here. I am going to say A and it is B, A to B, where we are given some force at the point A. Due to what observed, some vibrations are created. The particles which are in the metal, they are going to be vibrate. When they are making some vibrations, the sound is generated. Here the vibrations are transferred from A to B, because here if you can keep your hand, you can feel the sensation of vibrations after few seconds. So you have to observe, in any school or college, some iron bell is there. We are continuously striking it, but there is no loss of any mass in that metal, but it can produce this sound. In the same manner, here some particles are there, here solid particles. First they are going to be vibrate, and they can make some to and fro motion. Those particles, while they are making some to and fro motions, they can be collide with the surrounding particles. Again, during the vibration, they can pass the energy from these particles to this particle. Got my point? Once the solid is going to be vibrate, at particular region some particles are there. Those particles are going to be vibrate. While they are vibrating, they can make some to and fro motion, what we call generally it is like a oscillatory motion. They can make some vibrations or oscillations. So that's why here during the vibration they should be collide with the next surrounding particles. During that some energy is transferred from these particles to this one. Again same process, the particles are going to be vibrate like this. So this will be continued up to the last. So you have to observe where we are given some force, those particles are vibrate at that particular position only. Clear? Those particles are at must be their position only. They do not leave their original positions. They do not leave their original positions. But they can transfer the energy from one place to the another place. Got my point? When we are striking a metal rod, where we are striking the metal rod, there some particles are there. They can be vibrated and they can transfer the energy from their position to the next vibrating particles. During the vibrations, they will collide with each other. So like that, these particles should be next with someone, and like that. So what you have to say, the particles are vibrates at their respective positions only, but they can transfer energy from one place to the another. So this type of propagation of energy should be like here what we call wave motion. If the medium particles can takes energy from one place to the another place without leaving their original positions. Clear? Then that nature is what we call wave motion. Medium particles they can transfer energy from one place to the another place due to the vibration or oscillation, but they do not leave their original positions. They should be stand at their respective positions only, but they will make some vibrations. Clear? So here you have to notice it. The particles vibration, maybe it is in the direction of propagation of wave, or it should be perpendicular to the direction of propagation of wave. While the particles are medium particles are in vibration, their vibration may be in two ways. One is here nothing but it is parallel to the direction of propagation of wave, and some should be here in perpendicular direction. In the next, while we are discussing about the difference between the longitudinal wave and transverse, we will discuss very clearly. Okay, and in this example, the particles are vibrated, they can transfer energy from one place to the another place. Here in this example, the metal what we have taken, that should be nothing but it is a medium. It is a medium. So that's why you have to remember the sound waves must be required some medium to transfer energy from one place to the another place. Clear? Sound waves should be traverse energy from one place to the another place with help of the medium. Clear? For example, we are inside one glass room, completely closed. There is no propagation of air from inside to the outside. One fellow is inside the room and we don't observe and we lock the room, and after some time he was shouting, but we are not getting any sound, we are observing from outside. So like that, here sound must be required some medium, that means must be here in this example it is the rod, it is the example. So the sound must be transmitted through the solids, liquids and gases also. Clear? So here it is clear what it is, sound should be required medium. Is there are any properties for medium? To propagate the sound, the medium must be consist of three types of properties. The first thing is there should be having some inertia. The medium particles must be consist of inertia to store the kinetic energy. Clear? To oscillate or to vibrate. And second one, here they must be have some elastic nature. For example, it is the particle. Here one extreme position should be like this. This is the one extreme position. Clear? Where it is initially, that is the mean position, and it is now extreme position. So it touches the extreme position and goes to the another extreme position. So to continuous the vibrations or oscillations, that should be every time passes through the mean position. To do that, it's required some energy. That should be because of inertia it will gains the energy. And the second is what? Elastic nature should be there. When this goes to the extreme position, every time that should be crosses the mean position. That means what? Elastic nature it is there. For example, we are moving hand like this. where we are shaking like this, those molecules of air going to be disturbed. Once you can remove from the hand your position, obviously the molecules will come to the original position. That is what we call elastic nature. Due to any external force or deformation force, there is some change in position of the particles or molecules. If you can remove the force, again they want to reach the same positions. That is what we call actually elastic nature. That's why here, to continue the vibrations or oscillations, the medium particles must be consist of elastic nature. And third one is, the medium particles or molecules must be consist of, here, some frictional force, little bit frictional force among the particles. So these are the main properties for a medium. Look here once, properties of medium. Inertia, particles must be possess inertia so that its particle can store kinetic energy. Second one, in order to make the particles return to their original position, elasticity is compulsory, and there should be minimum frictional force between the particles of medium. This is simply about the what is wave and what is wave motion and what are the properties of a medium. Now let us discuss what are the characteristics of wave motion. Let's see what are the characteristics of wave motion. The first thing is, when the wave is passing through any medium, the medium particles can vibrate simple harmonically and they do not leave their positions and transfer with the disturbance. That is the first thing. And second thing, in the wave motion, the particles have different velocities with respect to the different positions in the medium. Clear? And third one, while wave is passing through one particular medium, the velocity of wave is same throughout the medium. It can be depend upon the nature of the medium. It do not depend upon the wavelength and frequency. How to understand the difference? In wave motion, the particles have different velocities with respect of different positions. Medium particles have different velocities. You have to notice it. And the second thing is what? In any particular one medium, the velocity of entire wave, remains constant, because the wave velocity or velocity of the wave should be depend upon the nature of the material, not on wavelength and frequency. And next thing here, during the wave motion, there is no loss of matter. That means the particles can vibrate at their respective only positions only. There is no moving of matter in case of wave motion. So these are the main characteristics of wave motion. Let's see here on board, already it is same thing it is there. First thing, when a wave passes through a medium, particles of the medium vibrates simple harmonically about their position. They do not leave their positions and move with the disturbance. Second one, in wave motion, the phase of the particles of medium keeps on changing. Phase of the particles also changes, and the velocity of the particles during their vibration different for different positions, and the velocity of wave motion through the medium is constant. Energy is propagated along the wave motion without any net transfer of matter. Here phase is varying from one position to the another position during the vibration of the particles. You have to notice it. And already we discussed what is the importance of wave motion. The energy can be transferred, energy and momentum both can be transferred from one place to the another place without leaving the original positions of medium particles. So these are the characteristics of wave motion. Now let's discuss about the types of waves based on the medium. Medium is necessary or not, like that. Based on the medium, the waves are classified into two types. One is the mechanical waves, and number two, non-mechanical waves. non-mechanical waves. Clear? Based on the medium requirement, the waves are divided into two types, mechanical waves and non-mechanical waves. Here for mechanical waves, examples are the waves produced in the string and waves produced in the water, so and all kind of sound waves which are required medium. Okay, they can be coming under the mechanic waves. And now non-mechanic waves, here for mechanic waves medium is compulsory, medium is necessary. For mechanic waves medium is compulsory, for non-mechanic waves medium is not required, so they can be called as non-mechanical waves. The waves which do not require any medium for their propagation, they can be called as non-mechanical waves. So here almost are here all electromagnetic waves and light waves, they can be taken as examples. Electromagnetic waves means X-rays, infrared rays, gamma rays, radio waves, like that, all are coming under non-mechanical waves. And next thing here, based on vibration, again these are divided like these two types. One is the longitudinal and next one is transverse. So based on vibration, so let's next coming topic is only difference between longitudinal and transverse, then we can clearly discuss. And next one, based on propagation, how the wave is propagated, based on that again the waves are classified into two types. One is the progressive wave, and next one is stationary wave. Here progressive wave means simply here the wave which is generated from the source, it can move in forward direction with respect of time and never come back to the origin. That type of waves are what we call progressive waves. In the next video we will discuss very clearly about the what is progressive wave and progressive wave equation, how it can be varies under different conditions, there we can discuss. And now here what is meant by stationary wave? Superposition of two progressive waves which are having same frequency and same amplitude, that should be called as here stationary waves. So simply here based on propagation, the waves are divided into types, progressive and stationary waves. And now next thing is based on dimensions. So based on the dimensions, again the waves are classified into three types: one dimensional, two dimensional waves and three dimensional waves. Based on the dimensions, how many types here waves are there? Three types: one dimensional, two dimensional and three dimensional. So one dimensional means the waves are moving with respect of any one axis, either it is x or y or z, any one of the axis. That is what we call one dimensional wave. Simply here waves produced in the strings, that is the best example for one dimensional waves, because when we can pluck the wire string of the any musical instrument, the vibration what it is produced, that should be moves along the string only. String means it is along the x axis, if it is vertical along the y axis. So that is the best example for one dimensional. And two dimensional, that means what? The propagation of movement or the wave is in the moving along the in particular one plane motion it is there. So that means here along the x axis, y axis, that means what? In particular one plane. In this case the wave is moving along the one particular axis only, here in the combination of two axes, that is what? 2D. So that means here the wave is propagating in the plane. And basic example that for that, waves which are moving on water surface, These are the examples for 2D, two-dimensional waves. And now three-dimensional. Three-dimensional waves means nothing but here, which are in the space, We are shouting, we are producing some sound, and there should be passes through the air, and there should be reaches to some other point here. So there should be passes in the air means what? Obviously that is three-dimensional. So if it is along the only one axis, one dimensional, in any particular one plane, that should be here two-dimensional, in any particular space, then that is what we call three-dimensional waves. And along with them, some other waves are there. Let's discuss. Let's see some other waves. Some other waves here. Matter waves, audible waves or sound waves, ultrasonics, infrasonics, shock waves. Here, what are matter waves? Waves are associated with the moving particles. That should be what we call matter particles. Matter particles means some massive particles. Along with the waves, some particles are associated. That type of waves are called matter waves. And now here, audible or sound waves. Based on the frequency of the sounds, they can be again classified like audible, ultrasonics and infrasonics. Here, the waves which has the frequency lies between 20 Hz to 20,000 Hz. This is what frequency range, what we call, that is the audible range. The sound waves which are having the frequency range between these two, that should be what we call here audible or sound waves. Clear? And now ultrasonics. The sound waves which are having the frequencies more than 20,000 Hz, they can be called as ultrasonics. Clear? In between 20 to 20,000 audible range, and more than the 20,000 Hz, that is the ultrasonics. If it is less than 20 Hz, that is infrasonics. Clear? Ultrasonics and infrasonics. Ultrasonics are more than the 20,000 or 20,000 Hz. So there are some uses for ultrasonics. For example, in any industry, there are big size of metals are there. To find out the flaws or breaks in the inside the metal, for them ultrasonic waves are used to find out the flaws inside the metal which is having more size. For them ultrasonics are waves used, and in sonar system also used, sound navigation and ranging. And third one, while we are taking some scanning in hospitals, ultrasonography or ultraphotography, for scanning purpose also ultrasonic waves are used, because to find out the tissues of babies. And now here, to kill the small animals like rats, frogs and fishes, also ultrasonic waves are used. And now infrasonics, they cannot be heard by the human beings because less than 20 Hz. And now here one more is there, shock waves are supersonic waves. Shock waves are supersonic waves. So we can use this word in case of jet planes. Supersonic, we can use that word. Why they are taken as called as supersonic jets? Because they can move with the speed of that is more than the velocity of speed of wave. That should be, the supersonic waves are moving with a velocity that should be greater than the velocity of sound. Clear? So similarly here, the waves which are moving faster than the velocity of sound, they are called shock waves or supersonic waves. And to find out the velocity of the supersonic waves, there is one unit is formed, is there, Mach number. Mach number is the ratio of velocity of source to the velocity of sound. Clear? Let's now discuss about the characteristics of longitudinal waves. Already we discussed what it is. Based upon the vibration of the particles, the waves are classified in two types. They are the longitudinal waves and transverse waves. First thing is here, longitudinal waves. how we can classify the waves as longitudinal waves? If the medium particles are vibrates along in the direction of propagation of wave, then that wave is said to be longitudinal wave. If the medium particles are moving along the direction of propagation of wave, clear, then what you have to say, they are the longitudinal waves. All sound waves are the best example for longitudinal waves, and in case of flute or open pipe, closed pipes, we are getting the sound waves because of longitudinal waves only. And next thing here, in case of resonance apparatus also, above the water surface some air column it is there. In that air column also sound produced because of longitudinal waves. And to transmit the longitudinal wave, the medium must be consist of elastic nature. So these are simply about the longitudinal waves. Let's hear. The first thing is here, if it is a medium, and these are particles vibrates. So like this. In case of a longitudinal wave, at some regions the particles seems to be crowded, at some places the particles are going to be separated by some regions. Clear? So these are very crowded together, and this is the direction of propagation of wave. The arrow mark what it is? Direction of propagation of wave. Clear? This is what? Direction of propagation of wave. Clear? So while the wave is moving in this direction, energy is transmitted in this direction only, then the particles are going to be vibrates like this in parallel. If it is a particle, medium particle, and that should be like this, that should be vibrates as right to left. It is the mean position. It is going to be like this and comes like this. So it is to and fro motion. That's why here in this case the particles are going to be vibrates along the direction of propagation of wave. The wave is moving in this direction and particles also vibrating in the same direction. Then only it is what we call longitudinal wave. In a longitudinal wave where the particles are crowded together, that should be called as compression. Clear? That means what? Longitudinal wave consists of compressions and rarefactions. This is the compression, and next one is rarefaction. Again it is compression and rarefaction. So rarefaction, how we can define it? It means that in a longitudinal wave where the particles are separated by some distance, then that should be what we call rarefaction. So this is simply about a longitudinal wave. The medium particles vibrates in the direction of propagation of wave, and that should be consist of compression and rarefactions alternatively. Clear? The particles which are in the compression, rare, compression. The particles which are in the compressions, they should be having same type of vibration. Then they are said to be in same phase. And that phase difference is 2 pi radians. The particles which are in the compressions, they are going to be vibrates same. Then they are said to be in same phase and they have phase difference how much? 2 pi radians. And similarly, these two also same thing, rarefaction and rarefaction. They also have same phase of vibration. Clear? And next thing is here wavelength. What is here? Wavelength. The distance between the consecutive compressions, any two compressions or any two rarefactions, that should be called here wavelength. Simply, what is the wavelength here? As for this one, distance between any two consecutive compressions or rarefactions. The distance between any two successive compressions or rarefaction, what we call wavelength. So clear? And now wavelength can be shown by the symbol lambda. So it is the wavelength. And how much phase difference here? 2 pi. And if we can observe the consecutive or successive compression and rarefaction, in those two, the particles having different type of vibration, it means that the particles can exhibit the different type of characteristics, then they are said to be out of phase. What is out of phase? Then phase difference is pi radians. So here compression and rarefaction, they have how much phase difference? Pi radians. When they have phase difference is pi radians, then that is said to be out of phase. So simply about this one is longitudinal waves. Let's go for transverse waves. See, now let's discuss about the transverse waves. What are transverse waves? Which waves can be classified as or known as transverse wave? It means that if the medium particles are vibrates in perpendicular to the direction of propagation of wave, then that wave is said to be transverse waves. If the medium particles are vibrates in perpendicular, in case of longitudinal, medium particles are vibrates in parallel. Now in perpendicular, medium particles are vibrates. For example, this is the direction of propagation of wave, and the medium particles vibrates like this. Yes, like this. So that's why here, that is what I have to say, transverse waves. If the medium particles vibrates in perpendicular to the direction of propagation of wave. Clear? So transverse waves are formed in the stretched strings. Water ripples also seems to be like transverse waves. Should be formed on the water surface, not inside the water. Transverse waves are formed in stretched strings, and they can be able to or formed on the water surface, top surface. They are not entered into the water. And next thing here, to transmit the transverse wave, the string must be have more rigidity. Clear? The string of the musical instrument should be going to be very tight. Rigidness should be more. Then only transverse waves very easily formed. Clear? So now let's see here. Transverse waves can be polarized. They can be polarized. Here polarized, nothing but what it is. The vibration should be confined to particular plane. Either it is vertical or horizontal. That should be clearly, we have to mention the vibration of the particles in case of transverse wave. And medium should have rigidity to transmit the transverse waves, and these are formed in the stretched strings. Now let's see here definition of transverse waves. Here this is the direction of propagation of wave. In this way the wave is moving. Clear? Then the particle should be vibrates like this. Yes, like this. It seems to be like this, like here. Clear? It is now transverse wave. This is what direction of propagation of wave. The medium, for example, if it is the mean position, the particles are vibrates once upward, once downward. Clear? The upper region portion, it is called crest, and downward is trough. Clear? Where the particles are vibrates in upward direction, that should be what we call crest, and it is trough. In case of longitudinal waves, we have compressions and rarefactions. Like that, here crest and trough are formed alternatively in case of a transverse wave. Clear? The definitions are similar here. The phase difference between any two consecutive crest or trough is how much? 2 pi radians, and the distance between these two successive crests or troughs, that should be called as here wavelength. That should be what we call wavelength. The particles which are in the crest, they should be seems to be like same type of vibration. That's why they have to said to be in same phase. That's why the phase difference is what? 2 pi. And here the particles which are in the crest and trough, both are in vibrating in opposite directions. That's why they are said to be out of phase. Then the phase difference is what? Pi radians. And the distance between any two successive crests or troughs should be called what we call wavelength. So this is simply about the transverse waves.
Now let's discuss about some of the important
terms which are going to be used in the chapter of wave motion. They are amplitude, frequency, wavelength, time period, and wave number, and here next one is phase, path difference, and speed of wave. So these are the main terms we have, and along with that some more are there, we have to discuss later. The first thing here, amplitude. Important terms regarding the wave motion. The first one is what is amplitude? Amplitude should be shown by the small a or capital A. What is amplitude? Amplitude is nothing but maximum displacement of vibrating particle. Displacement of vibrating particle is called amplitude, and that should be measured in terms of meters. Clear? To understand that simply here we are going to, for example, if it is a transverse wave like this, so transverse wave should be like this here. So this is the first time vibration and this is the second time vibration. So in this case the displacement is, for example, here this is the y1, I am saying this is the y2. Two waves are there like this, y1 and y2. Here what is the, which is greater one? y2 is greater than y1. So y1 is displacement and y2 also displacement, but y2 is more than the y1, and this y2 is, if it is maximum, that should be called amplitude. What it is called? Amplitude. Clear? The maximum displacement of vibrating particle, that should be what we call amplitude. So this is in case of transverse waves, crest has the maximum displacement, then it gives the amplitude. And for example, in case of longitudinal wave, if it is the mean position and it is vibrating in this like this, first time like this, and second time the particle is going to be distance like this. Now second time should be here, displacement is more, and that's what it called maximum displacement is nothing but its amplitude. It is in horizontal direction and that should be in vertical direction. Clear? And next thing is wavelength. What is mean by wavelength? The distance traveled by the wave in particular time period, that should be called wavelength. That should be shown by the symbol lambda. That should be measured in terms of meters or angstroms. Clear? The distance traveled by the wave in particular period is what we call wavelength. So the same definition is applicable for here longitudinal wave and transverse waves, but that should be explained in different manner. Look here now, already we discussed while we are discussing about the difference between the longitudinal and transverse. It is the transverse wave, crest, trough, crest, and next one is what? Trough. The distance between any two consecutive crest or trough should be what we call wavelength. And in case of a longitudinal wave, the distance between any successive compressions or rarefactions is also called as wavelength. Clear? That is the definition for wavelength. And frequency, that should be shown by symbol F or nu. F or nu. What is frequency? The number of vibrations made per second. The number of vibrations made by the particle in particular 1 second is called frequency. Clear? And that should be measured in terms of hertz. And what next one is time period. What is time period? The time taken by the particle to complete one vibration, that should be what we call time period. Time taken to complete one vibration is called time period. And wave number, the number of waves generated in particular one unit distance. The number of waves are confined in particular distance, that should be taken as wave number, and that should be given by the formula nu bar is equals to 1 by lambda, and its unit should be taken as meter inverse. And next one is phase. What is the phase? Phase can be identified by the symbol like this pi. The phase means here, that is the property that can explains the position and direction of vibrating particle in its motion at particular one instant. Phase can explains the direction and vibration of a particle. It is nothing but simply explain about the position of the particle while the particle is in motion. That should be what we call phase. And path difference. What is path difference? While they are moving in particular one direction or opposite directions, some two waves are there. If they are moving in the same direction or different directions, If there is any difference between their positions, their lengths, for example here this is the first wave and now this is the second wave, and now distance is what is here? Yes, path difference. The difference in the lengths of the wave should be called here path difference. And speed of wave, the speed of the wave is much, it means speed of wave can explain the how much fast it is moving in a medium, how much faster it is moving in a medium, the speed, what we call speed of wave. Simply here what you have to say, the distance traveled by the wave in particular time should be called as here speed of the wave. Speed is equals to distance by time. Clear? Let's discuss what is wave pulse. For example, here you want to understand the pulses and wave train. Simply you can take a rope or thread. One end of the rope should be tied to any rod and the second end of the rope should be in our hand, and now you can shake like this, then the rope should be moves like this. So generally what you say, wave movements. Clear? When we are taking a rope and there should be one end should be tied to the rope and we are having one end in our hand, and you can simply shake like vertical direction, that should moves like this. Here it is like a wave. Clear? In that, what is pulse? The disturbance created in the medium for a short time. Then the shortest wave is called wave pulse. Clear? The definition is clear here. Wave pulse, shortest wave produced in a medium when the disturbance created for a shortest time is called wave pulse. So this only here it is wave pulse. It is a wave pulse. It is a disturbance, and there should be here only the disturbance is for only short time. That's why we are writing only this one. Now it is called here wave pulse. Clear? And what is wave train? The combination or series of number of pulses like this, number of pulses. That should be called here wave train. What we call wave train. And next thing is wave front. What is meant by wave front? Simply here you can observe, in a steady water, if you can drop a stone or pebble, then what you observe, at particular one point the disturbance is created. That should be carried forward in all directions with uniformly. Clear? The disturbance is spreads in all directions. Then only what you get, water ripples are formed. Water ripples are formed. The ripple of water should be having equal radius in all directions. All directions. So that's why here water ripples are taken as the wave fronts. Here what is meant by wave front? From the point of source, the sound is generated, the wave is generated. So after moving some distance, at particular one line or one surface, they have equal phase. Equal phase. It is while the wave is in motion, at particular one line or one surface, the particles which are vibrating, they have same phase. The locus of all these points should be called here a wave front. Clear? So here it is the, look at the diagram here, this is the point of source. Point of source. That means what? We dropped stone at that point. Then what you observe? Water ripples are formed like this. Clear? The water ripples are moving in this direction we are taken. Clear? The ray is moving in this direction. So here some dotted lines are there. These are the lines or surfaces when the particle are there at particular line. They have same phase. They have same phase. That's why it is called wave front. What it is called? Wave front. Look here. A wave front is a line or surface on which disturbance has the same phase at all points. On that particular wave front, the disturbance is same and phase also same. Now let's see the relation between the frequency, wave speed and wavelength. Relation between frequency, speed and wavelength. Here in time period t, what is time period? Time taken to complete one vibration. In particular time period, distance traveled by the wave, distance traveled by the wave can be taken as lambda. Clear? So what we know, formula, speed is equals to distance by time. T is the time period, and in that time period distance traveled by the wave is how much? Wavelength, lambda. So then obviously we will take speed is the v and distance is nothing but wavelength, lambda, and by time means time period. So this is the relation between v is lambda and t. So relation between wavelength, time and speed. And now here we can write v is equals to 1 by t into lambda. We can write 1 by t into lambda. We can write 1 by t means what? Reciprocal of time period is what we call frequency. Therefore v is equals to nu lambda. V is equals to nu lambda. That is the relation between v is equals to nu lambda. Here what is v? V is the speed, and nu is the frequency, and lambda is the wavelength. Clear? So this is the relation between among these three factors, these physical quantities. Now let's see here one problem on that relation. Problem is there like this. Here what it is, the speed of a wave in a medium is 960 meter per second. The speed of a wave in a medium is how much? 960 meter per second. If 3600 waves passes through a point in a medium in 1 minute, then determine its wavelength. Here the speed of the wave was given how much? Speed was given v is equals to 960 meter per second. And what you are saying, how here 3600 waves are passing through this point. Clear? So the number of waves passing through particular one point in particular time is what we call frequency. That's why here nu is equals to 3600 waves per minute. Clear? So obviously what, right? 3600 by per 60, that is what? Number of waves per second. Waves per second is nothing but frequency. So here simply cancel 60. Nu is equals to what? 60 waves per second. Clear? Then what we know, what we have to find out? We have to find out the wavelength lambda. Clear? That is we have to measure. V is equals to nu lambda, and then lambda is equals to what? V by nu. What is V? Speed. How much is there? 60 was given. And frequency how much? Sorry, V is what? 960, and nu is what? 60. Here 0 cancel, 6 1s are 6. So lambda is equals to what? 16 meters. Now let's discuss about the equation of a traveling wave. Already we know that what it is. When a source of disturbance is at one point, that means wave is generated at one point, and after some time the disturbance is carried forward during the wave motion. That's why here, like a simple pendulum oscillations, it is a mean position, that should be goes to the one extreme position, and after that another extreme position. That means what? The displacement should be here varies from with respect of time. The position of the particle is varies with respect to time. For example, here it is a one transverse wave. Its position should be varies with respect of time. Now the direction of propagation of wave is what? Here S. That should be like along the x-axis. So that's why here the position of the particle should be here taken as function of x comma t. The displacement of the wave, that should be having two variables, x and t. X is the position and t is the time. These two are variable things. So that's why here the equation of a traveling wave should be given by the like this: y is equals to f of x comma t. F is nothing but here function of our variable things, we have x and t. That's why here in examples the displacement going to be having differentiation. we can write like this: dy by or dou y by dou t comma dou y by dou x comma dou square y by dou t square or dou square y by dou t x square, dou y by dou t, dou y by dou x, dou square y by dou t square and d square by dou x square, like that. So in examples there is possibility for here for derivations. And now here what I am saying, here y is equals to x plus t and y is equals to some here x plus t square and x cube, or y is equals to x plus t cube or x square, like that. So all these are the functions with respect to of the variable things x and t, but we have to say all equations are maybe wave or not waves. Here when we have equations, then it is going to be say it is this equation represents a wave and this equation represents a wave or not, like that. For that to say any equation is going to be wave, there are three conditions must be there. Clear? The first condition is the equation must be satisfies the condition dou square y by dou t square is equals to k into dou square y by dou x square. The equation what it is there, that must be satisfy the condition dou square y by dou t square is equals to k into dou square y by dou x square. When this condition must be satisfied here, that is going to be thing it is a wave, like that. Here k is equals to nothing but square of wave velocity, square of wave velocity. Clear? And the second condition is the wave must be have only one value for wave, even though x and t variable, even though position and time may be variable, but the wave must be have only one value. That is second condition. And the first derivative, third one is the first derivative must be continuous, that means we are one time it is going to be differentiate like this. And next thing here, next one also again there is chance for differentiation. So that's why here first derivative must be continuous, that means first differentiation, after that second differentiation is also possible. Clear? So when these three conditions are satisfied, then only the given equation is said to be wave. Look here, there is another formula, important formula it is there, it is important in problems. Look here, y of x comma t should be taken as f of ax plus or minus bt, like this. The disposition or displacement of the, here you have to remember it is related to the one dimensional, don't forget that. So here y of x comma t is equals to f of ax plus or minus bt, it is there. Now here in this case, here the wave velocity should be taken as the ratio of coefficient of time by coefficient of position, coefficient of time by coefficient of position, nothing but what it is, the coefficient of t is what, b, and coefficient of position is what, a. So therefore v is equals to b by a. In this way also we can find out the wave velocity in case of one dimensional. Clear? Now let's see one example problem on symmetry of wave pulse. So this is the based on symmetry of wave pulse. Wave pulse. This is the one of the important model. Look here, y of x comma t is equals to given by the form equation 0.8 by 4x plus 5t whole square plus 5 represents a moving pulse when x and y are in meter and t in seconds. Then choose the correct alternative. So here four options are given. In those which are correct and which is the wrong one, we have to identify that. First, A is the pulse is moving along the positive x direction, and B, in 2 seconds it will traverse the distance of 2.5 meters. And now its maximum displacement is 0.16 meters, and it is a symmetric pulse. So what you have to decide, if it is moving along the plus x or minus x, we have to select, we have to decide. In 2 seconds that should be traversed distance of 2.5 meters, and its maximum displacement is what, 0.16 meters, and it is a symmetric pulse. In case of a symmetric pulse, the displacement with respect of positive x-axis and negative x-axis both are similar. So from mean position to how much distance traveled along the positive x-axis should be equal to the from mean position to the distance traveled along the negative x-axis both are same. Then only what you have to say it is symmetric. So here I draw one diagram here. When time t is equals to 0, that should be having the maximum displacement. It is nothing but y value with respect of y axis. Clear? So after some particular equal time, that should be here having this is the minus x and this is the plus x. Clear? When both are similar, when both are same, then it is what you have to say, the pulse is symmetric pulse. Now first we have to find out the maximum displacement. When the time t is equals to 0, y value is maximum. That's why here at this condition t is 0 and x also 0. That's why here thought it is y of 0, x value is 0 and t value also 0. Here x is 0 and t also 0. Then what right here 0.8 by 4 into 0 plus 5 into 0 whole square plus 5. So 4 into 0 0, 5 into 0 0. Anything here it is what right 0.8 by 0 square plus 5 like this. Then what right here 8 by 50 we can write, 8 by 50 we can write. Clear? So simply now here what right here 2 4s are 25s are, that should be here nothing but 0.16 we will get, 0.16 we will get. So here 0.5 by 10, 0.8 by 5, that means what 8 by 50 will write, 4 by 25. So then obviously what here you get 4 25 0, 25 ones are 25, 5 1 5. Clear? And it is 0 again, 30 150. That's what right here 0.16. That's why here y is equals what 0.16 meters. That's why here third its maximum displacement is what 0.16 meters is the right answer, right option. And next thing here we have to check whether they have symmetry or not. They have symmetry pulse or we have to check. That should be nothing but here y of x is equals to y of minus x. When these two are equal, then obviously here there should be symmetry pulse. That's why here we will write y of x is nothing but here in that equation we are going to substitute here t value is 0. Then here 0.8 by 4 into x plus 5 into 0 whole square plus 5. Then y of x is what? Similarly here 0.8 by 4x whole square, 16x square plus 5. And similarly you can do this one, y of minus x also we will get same thing. Then what it is here 0.8 by again 4x plus 0 whole square. Then what it here, so we will get same thing here 0.8 by 16x square plus 5 will get. Therefore what write y of x is equals to y of minus x. That's why here symmetric pulse is right one. And next thing here third one, in 2.5 seconds it will traverse a distance of 2.5 meters. Our pulse is moving along the positive x direction. Among these two we have to check whether these two are right or wrong. Now let's check the pulse can move along the negative x-axis or positive x-axis. And what was given, it can traverse the 2.5 meters in 2 seconds. 2.5 meters in 2 seconds. These two are right or wrong we have to check. So for that here the initial condition is what, the pulse should be like this here at x is equals 0, time t also 0 and it is plus x and this is the minus x and the maximum displacement is what 0.16 meters. So in this case also when time t is equals to 1 second, the displacement should be taken as here minus 1.25. Position of is here what is minus 1.25 meters. And again we have to assume the same maximum displacement 0.16 meters. Clear? So 1 second 1.25. So here when the particle is moving along the negative x-axis, here obviously here what right 1.25 again minus 1.25. Then what you get here? 2.5. So obviously here 2.5 in 2 seconds we will get. Why? Because we will take speed is equals to here 1.25 meter for 1 second, or simply 1.25 meter per second. So when it is having the motion is along the negative x-axis only, it is possible. When x value is initially minus 1.25 and for 1 second, for next 1 second minus 1.25, then what you get here? Minus 2.5 will get. Clear? And if it is moves along the positive direction, then what, right? Minus 1.25 plus 1.25, then the value is going to be 0. That's why here what you have to confirm, in this case the pulse is moving along the negative axis, and that's why here it will covers the 2.5 meters in 2 seconds. 2 seconds. For 1 second 1.25, for 2 seconds 2.5. Clear? That's why given options, first one is the wrong one. What is the first one? The pulse is moving along the positive x-axis he was given. That is the wrong. Here it is moving along the negative x-axis. Clear? See the next example. This is the another model to find out the wave velocity. Look here. At time t is equals to 0, y of x equation of a wave pulse is given by y is equals to 10 by 2 plus x minus 2 whole square, and at time t is equals to wave equation is given by y of x is equals to 10 by 2 plus x plus 4 whole square. Find the wave velocity. That is the concept. What it is, when t is equals to 0, the equation should be here y is equals to 10 by 2 plus x minus 2 whole square, and when t is equals to 2 seconds, then what we write here, y is equals to 10 by 2 plus x plus 4 whole square. So here now, to find out the wave velocity, we must know about the displacement or distance. We have to find out it. So here, when the y value is becomes maximum, first we have to know. When we have denominator, in the denominator when we have least value, then obviously this value becomes maximum. So when at time t is equals to 0, if we can take x is equals to 2, when time t is equals to 0, if you can take there x is equals to 2, then y value becomes maximum, then y is equals to what, right? 10 by 2 we get. Similarly, at time t is equals to 2 seconds, if you can take x is equals to minus 4, then obviously here y value again becomes maximum. That means what? It is moving along the from here 2 to minus 4. If it is the origin, it is initially where it is 2. At t is equals to 0, x value is 2. And when time t is equals to 2, x value is here. What is? Minus 4. So if you can take the find the speed, here what is here? 2 plus and it is 4. Clear? The x1 to, and this is x2 and it is t1 and this is now t2. So what was given? Wave velocity we have to find out. So in this case we can write x2 minus x1 by t2 minus t1 we can take. So x3 is what? Minus 4 and x1 is what? 2 by 2 minus 0. That means what? Minus 4 minus 2 by 2. That is what? Minus 6 by 2. That is equals to here minus 3 meter per second. It is the wave velocity. Clear? Dear students, if you can understand this one, like, share, comment the video and subscribe my channel to get the all notifications and press the bell icon too. So from my side, my request is, if you are expecting more videos from my side, please cooperate and encourage my channel by sharing my channel to your friends. Thank you for watching.